Welcome, everyone. Let me start that again. Welcome, everyone. My name's Mark Hughes, and I'm part of the team at Advanced Assembly in Aurora, Colorado. And it is my great pleasure today to welcome Greg Zeraldo, the Senior Director of Operations at Advanced Assembly. I know what you're thinking. Is it that Greg Zeraldo? It is. We've got that Greg Zeraldo. Some of you have been fortunate enough to have the Greg Zeraldo sandwich in the fridge in the lunchroom, or maybe the Greg Zeraldo coffee, or the Greg Zeraldo iced tea. I know. You know that you have the authentic Greg Zeraldo merchandise when you hear Greg shout across the factory, "Hey, who took my stuff?" We've got that Greg Zeraldo, and it really is a pleasure to have him here with us. So, Greg, welcome, man. Thanks for coming.
Thanks, Mark. I appreciate it, man. Thank you so much for having me. I love to be here.
Hey, these introductions just keep getting better by the minute.
Literally, and at this point, it's literally better by the minute because we've gotten to do this twice now, so that's awesome.
Yeah. So, Greg, man, tell us a little bit about your background and experience, and then we'll get going in the webinar.
Yeah, I've been with Advanced Assembly running operations for the last 4 years. It's been a great experience. I came from the bare board world, so it was a nice little changeover to really dive deep into the PCBA side of the business. Prior to that, I was in a similar role with a large board manufacturer, and a lot of principal focus on high reliability, HDI, satellite, defense, all sorts of applications like that. So it's been a fun ride, and here we are.
Very cool, man. Before I jump into the high reliability, do you remember when we first met, you told me the story about what brought you into printed circuit board manufacturing, what you were doing before?
Yeah, graphic design.
Yeah. How did you make that transition? What brought you over here?
I came from a saturated industry of everybody and their extended family who was all of a sudden a graphic designer. There were graphic designers for print, graphic designers for web, and everything. And so I knew that I had to do something else. I knew that I could do other things. I just had to figure out what it was. And I had a friend of mine who worked at a bare board shop years and years and years ago. And every time we go out for coffee or catch up, it was always like, "Man, what do you do exactly?" And he would start going through the process of what it'd take to, start putting these things together. And I've always been very mechanical and very techie. And I've always really kind of thought that, how did that PCBA get into the Xbox? How did it get into my PC tower? How does it go up into space? How does it do things? And so I had a epiphany to where I literally dipped out of the industry that I was in basically overnight and took an entry-level job working for a board fabricator. And it was the wildest experience I'd ever had. 2 weeks into it, I was like, man, what did I get myself into? And I love every minute of what I do. It's absolutely just been a great ride, and I can't wait to see where the next 20 years goes.
So you went from a graphic designer to an expert in the field.
Yes.
That's
so many
nuts.
words. Yeah, it's a little bit of it's definitely certainly not the norm as far as how people get into the industry. It's one of those things in manufacturing, nobody really knows how things get there unless they know somebody who knows somebody. You know what I mean? People who are, building EVs, people who are, in the IoT world, people who are doing, space and defense and all those things and stuff like that. Nobody ever puts two and two together that somebody somewhere had to build something to build something. And so, being able to be kind of an integral part of that supply chain to our customer base is just the most rewarding experience in the entire world. I absolutely love it.
Yeah. Well, we brought you here today to pick your brain about high reliability electronics, both on the PCB side and the PCBA side. So maybe you could start telling us what high reliability is, what it means to you, and who needs it in their designs.
That's a great question. The simplest answer that I could think of with that, high reliability is quality. If you think about it, you look at every spectrum that you can possibly have, and you have, the spectrum of, the inventor, the maker that is working out of their basement, working out of their garage, working out of small space, maybe that they're leasing, all the way up to, the big boys and girls in the prime world that are delivering things that are payloads and rockets that are going downhole and everything like that. At the end of the day, every single one of those guys, it requires high reliability. They need their product to function. And whether it's going into, a Nest or a smart home device, or it's going into a rocket, it has to function. So high reliability to me is quality. And it starts there and it stops there. You can, take all the processes and squeeze them into one thing to get your deliverable at the end of the day. But if it's not built right, it's not going to be reliable. And so that's kind of what I want to explore today as far as looking at the quality piece of it and kind of pull that thread a little bit.
Okay. Well, as an educator, as an electrical engineer, as, a PCB designer, I'm a big fan of just taking my schematics, not my schematics, but my layout, and throwing it over the wall and saying, hey, it's your problem now. But that's kind of a dangerous way to go about things, because if I don't know what I'm looking for, if I don't know what high reliability looks like, what quality looks like, I'm just setting myself up for failure. So what advice would you give a new designer, somebody to go out and design for reliability, and then to contract somebody who can produce what I design?
Well, if we're going to go back all the way to the design phase of, the product realization, it starts with having to know what application your product is going into. If it's going to be subject to high stress, whether that's thermal stress, whether it's vibration stress, whether it's atmospheric stress, every single one of those things can absolutely deteriorate the reliability of that said product. And so really understanding what it's going into and where that piece fits into the next subassembly of whatever the final product is ridiculously important. So starting with that, and then also appreciating what your design, how it looks on paper. Everything from, if you're designing something that's going to be super robust, it's going to be going downhole, it's going to be exposed to a lot of, vibration and thermal stress and everything like that. Designing something on 1/2 ounce copper with, super thin pre-preg, just a really generic stack of it and everything like that is really not conducive to it lasting very long. From a functionality standpoint, electrically, it's going to be fine. But as soon as you start putting that PCBA to work, as soon as it's part of a system of something, it has to function in the environment that it's purposed to do. And so really understanding what it does and starting with that piece of the layout, because, you can have Gerber artwork, you could have all of your, all of your signals connect together, all of the pieces and everything like that. But if it doesn't have the meat and potatoes to it, it's just going to fall apart. I think that's just a really big piece to recognize at the entry level piece of it. I think a lot of, newer engineers, newer design engineers and layout engineers that are thinking about this stuff, they're looking for functionality. And in my experience, when we have, groups that come here, we have small companies come here, we have huge companies come here. And if that's kind of the one piece that they tend to forget about, oh my gosh, well, yeah, it needs to do this. So I probably should have this type of material. I probably should have this type of copper weight. I probably should have this type of line and spacing to make sure that it's robust enough to handle the environment that it's going into.
So a lot of fabrication house right now, on 1/2 ounce copper, they can do 3 mil trace and space, no problem, right?
Sure.
Totally
Yeah.
doable.
Yeah,
But what I'm hearing you say is that might not be what you want to do for a reliable design. What are some issues with being on the cutting edge of manufacturability as it relates to reliability?
The cutting edge of manufacturability is that you're really pushing that envelope on what that board shop can do. If you're at a trace and space width that is pushing the ability to do that, one, your yield is going to be atrocious. You're going to spend more money on remakes. You're going to spend more money on materials. You're going to spend, the board house is going to have to charge you more because remakes aren't free. They need to be able to incur that cost So if you want to design the slickest and fastest board out there, but you're not really appreciating what the application is going into, there's going to be a disconnect there as far as the design goes versus what the actual deliverable is going to do. And so it's inherently important to recognize that. The edge of manufacturability is, man, that is one of the most frustrating things in the entire world, because you have tech that is moving faster than the capability of manufacturing. So the world of, again, whether it's IoT or whether it's federal contracts or satellites or, or anything like that, what people need and what they need from a functionality standpoint moves light years faster than what an etcher can etch, what a drill can drill, whether it's mechanical or laser, what a DC or pulse plating tank can plate. All of these different things, need to be able to meet what the shop can do. Granted, different shops have different capabilities and everything, but you throw out the 3 mil line, 3 mil space. And I said, from a capability standpoint, that's kind of, everybody does that now. 10, 15 years ago, I was like, oh, wow, that's interesting. Give my attention. Now it's just kind of, it's a Tuesday. And so pushing that envelope is great from a, again, proof of concept and understanding what the functionality of something can be. But if you are really looking for a reliable and repeatable and manufacturable article, you have to look at your design rules. You have to look at the material availability, and really look at the DFM and DFA that your board house and your assembly house are giving you. A lot of the time, that is some of the most critical feedback you can get, because while these guys may not necessarily be in your work cell at your company, like a SpaceX or a Lockheed or a Tesla or something like that, these guys know board manufacturing and board assembly better than anybody in the world. And they're going to be able to give you that advice and say, look, I appreciate what you're doing here with your tolerances and your artwork and everything like that, but you need to understand that if it's going into this application, it's not going to work. You might have limited functionality into it, but 2 weeks later, if it's down in a hole drilling and it stops, that could be very well related to the design's not conducive to what the application is. At the same time with the satellite payload, if something is going into a rocket, if something is going into a satellite, if something is type of like an engine control of something, one, either lives could be on the line, or you have a satellite that's up in space that you can't pull down and fix. It's got to work the first time, every time.
Totally. I brought up 3 mil trace in space as an example at the latest trade show. I think that was PCB West. I was standing there and a customer came up and asked if we could do 13 micron.
Yeah.
Yes, we can.
Sure.
But you might be uncomfortable with the number of zeros that you're going to have to write.
Absolutely. That's the thing, is that like, I guess it kind of comes up to the, the question of, can you and should you, right?
Yeah.
Just because you can doesn't mean you should, right? And so I think, that's where, the tech is to me light years ahead of the capability of manufacturing. There is companies in Asia that can get down to just ridiculously small lines in space and everything like that. But it's not going into an application, not necessarily that I know of per se, that's part of a bigger system. That's part of a bigger system. I mean, a lot of this stuff is really, you're looking at stuff that's at, for our iPhones and everything like that, for our phones and everything. It's some of the stuff is throwaway stuff at the end of the day. I mean, my phone, in a couple of years, I'm going to toss it. It's no big deal. Like I said earlier, you're not pulling a satellite out of space. That thing, 15 to 20 year, 25 year lifespan, if not longer. They have to deliver. They have to work.
So what would you say are some minimum recommended best practices as far as copper weight, plating thickness, material, stack up, just anything you can think of? What would be, you'd say, the bare minimum for something that improves the reliability over something I can go buy offshore, for cheap?
Minimum reliability, I think, is conducive to looking at what the capabilities of starting with the fab house. Obviously, that's where the magic starts to happen. It's and everything begins there. If you're looking at a manufacturer's capabilities and you're looking at their basic tray space widths, you're looking at the materials that they offer, not the exotic materials or anything like that, but the standard, 370 HRs, polyamides and stuff like that. Those are the most available and robust materials that are offered today. They're less expensive. They're a little heavier. So, I mean, if you're looking for, a lightweight material, it's not necessarily the first place to go to. But these are materials that are proven over and over and over again in a variety of different applications. And so, again, it's kind of, I don't want to say it's going and conforming with what's available just because it's there. It's there because it works. It's proven. We're not trying to reinvent the wheel here. The PCB itself, from a manufacturability, should not be reinventing fire or the wheel. The output of what it does could certainly be doing that, but designing within simple design rules that the fab house and the assembly house offer are the easiest ways to ensure reliability, something that's cost effective, and something that's manufacturable.
Fair enough. Let's say that somebody came to you and they were designing something to go downhole, right? Down a borehole. What are some characteristics of that design that you would expect to see?
From a design standpoint, it's going to be heavy copper, thicker dielectrics, thicker materials, and that's all going to be starting with your stack up. For conversation purposes, I don't really have specific numbers or anything like that, but I mean, really looking at making sure that you're not using 1/2 ounce copper. You're not using the thinnest, pre-preg stack up available or anything like that. You're building, you're putting your sandwich together to make it robust. That's the simplest way that I can put it. On the assembly side of it, I think is where it starts to get a little interesting. And so, assembly at its bare form, you're putting parts on boards and using paste as the glue, right? And so there is, whether you're using stencils or paste printers and everything in between, there is a certain amount of solder application that goes onto the SMD pad. It's going to go through reflow. There is going to be a solder joint connection at that point. What we often find, especially with our industrial customers and our downhole customers, is that solder connection needs to be more rock solid than anything that's going into space, anything that's going into a car, and everything in between. And so what we typically offer those customers is a completely different solder paste profile than what we would offer, a standard commercial customer. And we're able to do that. We don't use stencils. Everything that we do is actually printed with a jet printer. And we are able to add and subtract paste at certain really critical connections and critical components to make sure that the solder joint on there is rock solid. It has to be, especially when you're looking at vibration, thermal cycling and everything like that. It doesn't have the opportunity to lift a pad or break a lead because it's exposed to that. And so we're able to offer, a 100% over solder paste on what was previously applied on the SMD pad. So if you have just a base layer of paste that's put on there, we can increase that by 100%, by 200%, by 300% to really give a really robust solder joint connection while still mitigating shorts and solder balls and everything like that. That's huge. The flexibility to be able to do that from a design standpoint, from an engineering standpoint, to be able to offer something like that is pretty cool.
And then I understand you guys also put that through the vacuum vapor phase reflow process. Yeah, can you tell me a little bit about that and why it's better than, say, a convection or certainly an infrared?
Certainly. So to put it down kind of in layman's terms, for the guys that don't understand reflow quite well, and there's guys that do understand it, conventional reflow is a mechanical system. It's a chain-driven conveyorized belt that goes through a 9-zone oven, and it's got pre-soak areas. It's got your full ramp up to your full reflow temperature, and then it's got a cool down as it comes and exits out of the oven itself. It's a great piece of equipment, and for 75% of the world, it's a completely from a process standpoint, it yields a good quality. There's not a whole lot of voiding on it, but there's other customers, especially who, are looking from a high reliability standpoint to have, next to zero voiding on a bottom terminal component. If somebody needs that extra push of a full connection to the thermal pad or a bottom terminal SMD pad, vapor phase reflow is a great option. Vapor phase uses heat and vacuum to actually transfer the paste to its liquid state, to its solderability to the part as it exits the chamber. And so it's a much smaller piece of machinery. And what it uses is it uses an isolated chamber, and it uses a chemical reaction that causes heat and vacuum to essentially reflow the paste and also pull down the component while removing and sucking out all of the air bubbles that are trapped inside the paste when it's going through that. It's a really cool process. And so where you can have, 75% voiding on a standard conventional reflow process, you can get down to 95, 98% void free, if even better, depending on the design of the bare board on your PCBA. So it's a pretty cool piece of equipment and a lot of different things you can do with it.
Very cool. One of the issues that I've had with designs in the past, and I think I've sent you pictures of these, when I go through conventional reflow, is potato chipping. Things. Would you attribute that to uneven copper stack-ups? Would you attribute that to uneven dielectrics? What causes that, and how can I prevent that in future designs?
You're talking about potato chipping, you're talking about board warpage?
Yes.
Okay. So yeah, it's 100%. That's absolutely a stack-up thing. It starts and ends there. From a stack-up standpoint, your most elementary rule of thumb is making sure that you have an even stack-up. Regardless of what copper weights you're using, if you're using 1/2 ounce copper, if you're using 4 ounce copper, as soon as you introduce an uneven stack up to where your component side of your board is 1 ounce versus 1/2 ounce or 2 ounce versus 1/2 ounce, you're immediately going to show warpage as soon as it goes through its first thermal cycle. If your layout, if your stack up really needs that uneven copper weight stack up, just be prepared to understand that there's going to be bow and twist that's going to be introduced, warpage that's going to be introduced to that as soon as it comes out of reflow. We even see, especially if you're using a process like hot or solder level for your final finish, you can take a panel out of the Hassel machine, and it's just the entire panel is potato chipped. So before you even go to your first reflow profile, your first thermal cycle in PCBA, it's already warped like that. And so even trying to place components on a board that has bow and twist like that, just out of the gate from the fab house, is impossibly difficult to work with. Oftentimes it creates just other defects during the manufacturing process. Sometimes it even creates to the point where it's unusable. And then, going back to, the design standpoint, it's like, understanding what that does and mitigating that up front. So we're not coming back to you weeks later and saying, hey, guess what? We got these boards, man, we can't use them. Can't put parts on them. I can't put them through reflow. I can't get a fixture on them. I can't even put paste on it because there's bow and twist to it. There is just, it's looks topography on its nuts. So yeah, big problem.
Okay. So I didn't even really ask a reliability. That was just a basic usability question then. Mm-hmm. What about, you've talked several times about heavy copper, 4 ounce, whatever.
Sure.
Would you say it's better from a reliability standpoint to use a smaller base material with greater plating, 1/2 and 1/2, or large base material with smaller plating?
That's a great question. I'd have to think about that for a minute. What have you seen in your experience?
I don't use heavy copper.
If you're designing something.
Sure.
Yeah, if you're designing something, I'm going to go back to balance. There's no point in putting something, if you have 4 ounce copper and you're using a very, very thin substrate, or if you're using a very, very small dielectric, it's not conducive. It's not going to work the way you want to. If you have small dielectric, thin dielectrics between it, you're going to have crosstalk between your layers. You can create high resistance shorts in between your layers. So there's not even a physical short in there. It's just going to fail test. You know, on the opposite side of it, if you have, you know, ridiculously thick material, but you have thin copper, I don't know if it's necessarily going to be a bad thing from a reliability standpoint. It's just, you know, there has to be balance in between. I think that's the best thing that I can really answer your question with, Mark.
Okay. Yeah, no, the thickest I've ever used is 1.5, which I don't think necessarily qualifies as heavy copper. I mean, it might be on the threshold, but you know,
getting there. I mean, it's, yeah, for sure.
Well, that's interesting. All right. What other assembly gotchas do you see people doing and you're like, man, that ain't going to work, or that's going to really affect yield, or that's going to require an expert operator to, you know, hand walk through every step of the process. Yeah. And you're just like, why are people doing this?
That's a great question to ask, and one of the easiest questions I can answer. VMPad. That kind of covers two things. It covers quality and it covers high reliability. A lot of the designs that we see that come through, especially the early designs that we see, even though they may be going into something that requires high reliability, designers are not taking into consideration the VMPad issue in an SMD pad. There's bottom terminal or thermal pads that have vias that go right through them. These vias aren't capped. And where there's a hole, a solder will find a way to get through it. When it's going through reflow, as soon as that gets to its liquid state, the solder is just going to get sucked and wicked right into that hole, and completely removing any robust connectivity to that bottom terminal pad or that thermal pad. I cannot stress enough how important a via and pad design is filled and capped and plated over. You know, and even some of the, the smaller customers, or, the guys who are just kind of getting their design going and everything, they're like, oh, we'll get, a via filled and plated down the road, or maybe a budget allows, or, but the problem is that the effort and the work that goes into reliably producing a PCBA with unfilled VMPad designs is you're introducing a ton of rework to something. And while rework is kind of a day-to-day kind of back-end process in the PCBA world, you know as well as I do that nothing is ever built better than the first time you do it. Okay. So if you're placing a bottom terminal component, if you're placing something that requires that connection on there, if it goes into X-ray and we see that it has voiding all over the place, but the design also has VMPad that is not filled, that's an immediate kick over to rework, where oftentimes we have to use a rework machine to remove the component, add solder to it, work other areas of magic in the process to be able to get that bottom terminal component to an IPC acceptable standard. Guys who are designing things, if you have VMPad in your SMD pads, please fill them. That is the best advice that I can offer you, because it is going to save you a world of heartache, a world of cost, and your design is not going to function the same as it is. If you have a loose connection on something, and just because you want to get it out and get it back in your hands quickly, versus spending a little bit more money and spending a little bit more time and doing it right the first time, night and day difference as far as what your deliverable product is going to do.
I hear you. Yeah. If you're using a thermal pad, gosh, is it, I always get the IPC numbers. There's so many of them. Is it 7351 that covers that, or 2581? I don't even know.
I don't know if that's off my head. Yeah, that's all you.
On a good day, I remember that stuff. Most days aren't that good. And then if you were talking about a signal or whatever, just move the via off to the side. Give yourself a minimum web of, say, 3 to 4 mils for the solder mask to act as a dam. That'll keep the solder on the pad and from moving down the trace into the via hole and upsetting your assembly house, because they're going to charge you for it. And they're going to be playing, a little game of arts and crafts over in the corner with Kapton tape, trying to make it work for you. It ain't going to be pretty. It's going to look good. So, all right. I'm going to ask you another question, but while I do, let me go ahead and open it up to questions for our participants. you should have a Q&A down at the bottom of your screen somewhere that if you'd like to go ahead and click on and ask Greg or myself any questions, I would be more than happy to answer them for you. We've got quite a few people that we've seen in previous webinars. I recognize some names, so welcome and thank you for joining us. So what about packages? Are there any particular shapes and sizes that you would consider higher reliability than others? For example, would you recommend that somebody use a TSOP instead of a BGA or another unleaded component? Would you recommend that somebody use and again, this is just for example, an 0805 over an 0402 to SMD rectangular package? Are there anything there where I guess you see less failure on the assembly side?
From a package standpoint and a component standpoint, no. Where we see the failure actually happening is the layout of the pad size itself. Okay, and so regardless of what type of component, passive, active, all the things and stuff like that, every single one of those, we've never really had issues with, it coming apart, having issues under thermal when it's going through reflow or rework or anything like that. Even washing, just the abrasiveness of it going through the wash cycles and everything like that before we get ready to deliver the boards to QA. What we often see where the failure comes from is at the design standpoint of just not getting a big enough SMD pad for the connection. We see 0402s that have pads that are too big and too far apart, where there's basically you have two solder molecules holding hands connecting each lead of the part. You have BGAs that have your circular pads that are too small. You have rectangular leads for your leaded parts and everything like that are either too close together or they're too small, and so it doesn't allow enough volume of solder to be applied onto the pad itself. That's where we see the biggest issue. And so what I really want to make sure that everybody understands from a design standpoint, if you're designing, and if you're at that level of design and you know what your BOM is going to look like, you got a rough idea of what components are going to be populated onto it, is making sure that you're doing a really thorough review of the data sheet of the component, because that data sheet of the component is going to tell you exactly how big of an SMD pad needs to be there, how much meat on the bone needs to be there in order to have a robust solder connection. A lot of times, I don't think people look at that, or they don't look at it as in depth as they should, because some data sheets are 10 pages long. I get it. It's a lot of content, but it is so critical to understand how big of space you need, how much material you need, how much copper you need to be able to effectively solder that lead to and still have the connection that's going to last you until the board's no longer needed. So if I were to offer any suggestion to it, it is absolutely the design of the SMD pad.
Okay, well, thank you, Craig. And we do have our first question. For fine pitch devices, do you put the same amount of paste as you would for a normal device like a resistor? I'm thinking about the risk of shorts.
That's a great question. The answer to that is no, absolutely not. And so if you have something that's fine pitch, the volume of solder that's applied to that versus what's going to be applied to a standard resistor or capacitor is two completely different things. Now, the guys who are, using stencils, they're going to be, you're going to use a change in apertures. There's going to be a change in actual stencil thickness to mitigate those types of things. I would say less than 5% of the work that comes through our facility uses stencils. So I'm going to speak from a paste printing viewpoint. Like I said earlier, we are able to add and subtract paste on the fly. So when something is going through our paste process, we're able to import the actual solder paste Gerber layout. We're able to see all the different types of components that are going to be placed on this PCB. And from there, we can make changes literally at that time, at that workstation, to add or subtract paste. If you have something that has a default paste application and say it's full solder, 100% of the SMD pad is covered, but we know that by looking at that it's either a fine pitch part or the SMD pads are too close together and there's going to be bridging and we don't want to deal with that in rework. We can immediately assess that, reduce the paste just in that specific area, Just either we can do it by decode, we can do it by the aperture size, we can do it just isolated for that component only. And it gives us the flexibility to where we can really take a solid look at the design. We can look at what this is going to translate to in the PCBA and ensure that we don't have to deal with that after reflow. When we go to X-ray, the last thing you want to see is bridging, because then it's just more time.
Totally makes sense. All right. Hopefully that answers your question. And I'm sorry, my eyesight's not big enough to allow me to read your name, but thank you so much for asking. Do we have any other questions? If not, we'll let Greg get back to his very busy day. But Greg, man, this has been great. I've learned so much. Thank you so much.
Yeah. Thanks for having me, Mark. I appreciate it always.
Well, before we let you go, because we might have one more question floating out there, do you have any other final thoughts on reliability?
I could speak for hours on this, guys. You know, from a reliability standpoint, again, stressing, understanding what your application is going into, what you're designing for, who you're designing for. Is your final product going to be able to stand up to what it is going into? Being able to have an open and honest conversation, relationship with your board house, with your assembly house, speaking to the engineers there, speak to your production guys, getting on a call. We work so closely with our customers to where if they have a question about something, we can immediately facilitate that to our engineering department, to process engineering. I myself can facilitate these things. You know, there's not a lot of black magic that goes back behind closed doors or anything like that. It's just specialized processes. And so the more you understand the processes that go into how these things are built, is you can further understand what it means to design something for high reliability. There are certain processes that are just, they go down a different path. And so being able to understand what path you want your PCB to go down from a fab standpoint to an assembly standpoint is really key.
All right. Well, thank you so much, Greg. It's been a pleasure speaking to you, as it always is. And
Thank you
for joining me today. I've got a prize for you.
I want that sticker.
I'm going to send a sticker your way, Greg. So, hey, that's, we really need to get some of you going too here. Pass those out to people who come just for Greg Zeraldo. That's right, folks. The Greg Zeraldo.
I'll put that on my laptop. I want that.
Hey, man, no, it really was fun.
Yeah, thank you, Mark.
Sure. Any of the viewers out there, I do have office hours coming up in, I don't even know what time it is right now, probably about 5 or 6 hours on the Advanced Assembly YouTube channel. This recording will be available apparently at the Royal Circuits YouTube channel. We're covering our bases here today. But it was really great. Thank you, everyone, for joining us. And we sure hope to see you next time on, I'm trying to think when our next webinar is. Isn't it, aren't we together again on the 10th?
That's a great question. We'll talk after.
Or the 3rd. Yeah, we're getting back together here pretty quick. It's not going to be long. We're going to be over at Hackaday doing a hack chat. So keep an eye out for Dan Maloney's hack chat, and hopefully we'll see you there.